Before we really start, as a small remark, I did a presentation with the same subject in the beginning of this year on FOSDEM. Maybe people attended that one already. In that case, there's not so much difference this time, so feel free to leave again. There's one thing I want to say, that is this URL, which I'll come back to in the presentation itself. So, we develop embedded products, we have nice ideas, we work a lot to make a product, and then we install it on the roof of our company, for instance, for this GPS receiver. But then the product is sold, then people will install it in completely different circumstances, for instance, in the middle of the ocean. Now, no worries so far, except then you notice that you have introduced some bug in the device, in the software, so you want to upgrade the software. Now, if you're a bit smart, you have foreseen a mechanism to upgrade the software remotely, so you don't have to take a ship up to the middle of the ocean to do the upgrade there. But then something may go wrong during the upgrade. And Murphy's Law says, if something can go wrong, it will go wrong. Maybe not immediately, but eventually there will be some device that is broken. And you end up with a very expensive brick in the ocean, which is not what we want. So what we want is the ability to upgrade without bricking. My name is Arnoud van Capelle, and I'm a consultant for Mind. And as a consultant, I see many different environments in which this and other problems occur. And this allows me to get some kind of best practices for upgrades, and that's what I'm sharing here. You can download the presentation from our website, and it's under the CC by Z license, and I actually would like you to reuse this, maybe not the slides, but at least the ideas to using your own products, but also to convince other people to think about how to do upgrades. Now, how are we going to make our upgrades safe? First of all, we need to know what can go wrong, because Murphy's Law says if anything can go wrong, it will, so you have to know what can go wrong. So I will discuss some failure mechanisms, not all possibilities, but just some frequently occurring problems, and explain what you can do about those particular failure mechanisms. And then I have two separate subjects which are somewhat related. The second subject is upgrading the bootloader, which has its own set of problems. And the final subject is upgrading using a package-based mechanism. For now, I will assume that we will upgrade the entire firmware, so the entire kernel plus root file system combination. So what can go wrong? The first thing that can go wrong, and that people do think about usually, is power failure. When power fails on your device, then typically the device will just restart when power comes back again and all works as normal. But what when the power fails during an upgrade, then your new firmware is only half written. So you have half a firmware which is not going to do much good. To solve that, you have to make sure that you always have some working firmware. So, well, you need several steps for that. First of all, you need to add failsafe firmware. You need to have the possibility to fall back on something in case you have half-written firmware. Second, you also have to detect that the firmware is half-written. And that implies that you will need to do some kind of introduce some kind of atomicity in the upgrades. And that again implies that you will need some kind of journaling for write voltages. So how do we detect a power failure? Well, for that, in a normal process, you boot firmware. Now, before starting the upgrades, because of course, when you boot up, you never know whether this was due to a power failure or just due to somebody resetting the device intentionally. Or maybe it was a power failure, but not at a critical point. So to detect the power failure, before starting an upgrade, we will switch to failsafe firmware, meaning we will not reboot to failsafe firmware, but we will tell the bootloader to, next time you boot the failsafe firmware instead of the normal firmware. And this has to be done, of course, in permanent storage. So in the flash or in the hard disk, if you would have that, whatever that the device where also the firmware itself resides. So when you, after switching to the failsafe firmware or telling the bootloader to switch to the failsafe firmware, then you can start overwriting the existing firmware. In the middle of that override, something goes wrong. The power goes out, it comes up again, and next time you boot, you will end up in the failsafe firmware. And what is that failsafe firmware? Well, it's something small typically, or it could be an entire firmware image, but it can also be something very small. The only thing that it really has to be able to do is to do an upgrade. So the failsafe firmware will re-download the upgrade image, or it will just have the interface so that the user can upload a new firmware image. In the end, the failsafe firmware will restart the upgrade and again override the firmware image with the new firmware. And then after a successful upgrade, either by the normal firmware or by the failsafe firmware, you again tell the bootloader to switch back to the new firmware. This all sounds very simple, but telling the bootloader to switch is itself also something which is subject to failures. So how can you tell the bootloader to switch to something else? Well, for instance, if you have grub or Linux, what you will do is you write a file which tells the bootloader what to boot, so you overwrite that file with some new information. But if the power fails during the overwrite of that file, even though it's a very small window of opportunity, it's possible that the power fails during that overwrite, you're again stuck with a dead system. So to avoid that, you have to make sure that at some level that overwrite is atomic. And for instance, with grub in Linux, you can do that by overwriting it not directly writing into the file, but using the rename, because the rename at the file system level is guaranteed to be atomic. Of course, then you still have the problem that the file system data may be not in sync with the disk data if a power failure occurs somewhere. So you have to mount with the necessary barrier options and use a journaling file system so that at least something correct is on the disk. So the barrier makes sure that when you have synced it, that you're sure that it actually is on disk before you start overwriting the old firmware. In U-boot, so when you're booting from flash typically, the typical way to overwrite or to change the boot, what to boot is to overwrite the U-boot environment. But then if the U-boot environment is gone, this is catastrophic. You basically have no U-boot environment anymore, and U-boot doesn't know how to boot. Yes?
You have redundant environment by default in U-boot. So you have to overwrite twice to be catastrophic.
Yes, indeed. So U-boot does have a feature to have a redundant environment, means 2 copies of the environment, and U-boot checks whether the CRC of the environment is correct, and if it's not, it will fall back to the second copy of the environment. So that's indeed another option if you use U-boot. The message here is that you can do this, but you have to do it smart enough. You have to know how to do it in a way that also the switching of the boot, the selected boot image is atomic. So now is the new thing compared to my presentation at FOSDEM is that I have started to collect the infrastructure to make it easy to do this in a good way in a new project called GUPPIes, which stands for Generic Upgrade Infrastructure for Embedded Systems. The idea is it's actually very difficult to make a generic upgrade system because almost everything depends on which components you're using. So it's different if you're using U-boot or grub. It's different if you boot from flash or from an SD card. It's different if you use a flash file system or an export file system. There are a lot of dependencies on the actual processor, on the actual hardware that we're using. So it's difficult to make something which is really generic. Instead, I would like to collect pieces of scripts, pieces of code that can be used to compose an upgrade mechanism. Now, I had hoped to have this in a releasable status by this time when I would announce it, but of course real life has kicked in and I haven't had much time to actually do that. So right now it's pretty much empty, but I'm planning to, whenever I need something and I develop something for upgrades, I'm planning to put it in there as well. So what will be in there is scripts to generate boot scripts and to generate boot scripts which will guarantee that atomicity. And so you'll have separate scriptlets for when you have a grub bootloader, or when you have a U-boot bootloader, or when you have a barebox bootloader. It will also have the bootloader configuration, so the environment variables to use those boot scripts and fall back to the failsafe modes. And it will have the skeleton, so the pieces that you need to write an image to flash or write an image to SD card or whatever. So that was the first failure mechanism, power failure during your upgrades. The second failure mechanism is bad firmware. The idea is that when you install a new firmware image, hopefully you have tested it already. But you've tested it in one particular environment. For instance, you've tested it when using a DHCP server to get an internet connection or a network connection. But you never thought of testing it with a fixed IP address. And maybe it turns out that in your new firmware, a feature that a customer or a user is relying on for doing upgrades does not work anymore. For instance, the custom IP, the fixed IP address doesn't work anymore because you're not reading the correct configuration file. So that means that after running that new firmware, the system boots up, and so for the bootloader it looks like this is correct firmware because it's been completely written, but in this new firmware you can't do upgrades anymore, which is not as bad as a really rigged system, but it's almost as bad, so it's a frozen system. So what solutions do we have there? Basically you want to fall back on the previous known good firmware, or you could fall back on a failsafe firmware in case that the current firmware image is not good. So again, the failsafe firmware. And then, of course, you have to detect that it's known good. There again, there's no generic way to detect whether the firmware is good or not. Basically, you have to be sure that your kernel and root file system, your firmware, is booted and that it is able to accept new upgrades. Of course, in case there is a kernel panic or a system freeze or whatever somewhere in that process, there's no way to reset the system manually. So you will want a watchdog that automatically, where the hardware will reboot the system in case something goes wrong. And from the firmware, you just trigger that watchdog to see on that everything is still okay. And then also from the firmware, you'll tell the bootloader when the firmware is considered to be good. This one I'll come back to later. So the process then looks like this. Here I've included the second non-boot firmware image, so we have two complete copies of the firmware, but in general you could have more than two firmware images, or you could leave these out and just fall back on the failsafe in case that the firmware is considered to be bad. So what happens, we boot our new firmware normally. The new firmware, after a while, it resets because of a watchdog timeout. So it goes back to the bootloader. The bootloader now, somehow, I'll go back to that, notices that the firmware was not boot. So instead of booting the normal firmware, it will go to a fallback, namely the boot firmware. If that one also runs into the watchdog timeout for some reason, it will in the end go back to the final fallback and failsafe firmware. That's what I just explained. So how does the bootloader know that the firmware is not good? Well, it has to have, there are two options. Either it can detect that there was a reset due to a watchdog timeout. Most processors have that feature that you can read out a reset vector, and based on that reset vector, you know why there was a reset, so whether it was a raw reset, called power on reset, or watchdog reset. And so if it was a watchdog reset, then you fall back to the boot firmware. That's one option. Another option is to have a counter in the bootloader that will count how many times you have booted the system and fall back in case you've reset more than 4 times, for instance. That counter should obviously be something which is not stored in permanent storage, because when the system powers off, this is not because the firmware wasn't good. When it powers off, it was because of other reasons. So this shouldn't be considered as bad firmware. So when the system powers off, it shouldn't fall back to the fallback. So the boot counter is typically stored in on-chip RAM, for instance, or in some backup register. And you would, for instance, have support for such a boot counter. The advantage of a boot counter is that you can only fall back to the previous version if it fails a couple of times. Because it could be that you have a transient error, and then it will be repeated that if you're falling back to failsafe firmware, you basically lose all functionality of your system until the failsafe firmware decides to try again to load the normal firmware. But so you could spend a lot of time with a system which is still alive but not functional anymore. Well, actually the firmware is good enough to function, it just had a transient failure. So how will this be integrated in guppies? Well, it will again have scripts to keep track of the valid firmware images, so counting which firmware, keeping track of which firmware images exist on the system. We have something here. I always show a firmware as one blob, but typically a firmware consists of several components. So a kernel and a root file system to start with, but maybe even your root file system is split over several file systems, which can be upgraded together or separately. So both in the for the power failures and for the failing firmware, you need to keep track of which components have been upgraded and which components belong together. So there will be scripts in there to keep track of which components belong together, so which is the order of fallback between them. And so if there are old components which used to be in Flash but can now be recycled or overwritten by a new upgrade, to also keep track of that. Because of course with this no-boot firmware, if you're booting the no-boot firmware and you do an upgrade, then it should overwrite this one. But if you're booting this one, then it should overwrite the other one. And if you're booting this one, then it should overwrite one of the two, and you have to decide somehow which of the two. And then the final issue are the communication errors. So we're upgrading remotely. That means there is a channel going from the user that pushes the upgrade or the server that serves the upgrade to the device in question. Now, while you're doing the upgrade, something can go wrong in that channel. A bit can be toggled or a block can be lost. Or maybe there is somebody evil that injects something wrong in the stream. In practice, it's usually not somebody evil, but just somebody stupid that injects something wrong in the stream. But so there's a possibility that something goes wrong there. There, it's very easy to solve that. You just validate the image before writing it to disk. And with GPG, you can do validation really, really easily. To generate the image, you have a private key, and you sign your file with a private key. And then to verify, you have just this command. You use GPG and a pipe. You pipe in the file, you pipe it out directly to your storage. In GPG, it will tell you afterwards if the image was correct or not. If the image wasn't correct, you consider this the same as something went wrong during the upgrade, so you just restart. Of course, you have overwritten your old firmware on the way, so you still have to have some way of recovering from that. But as we've seen before, we already have a way to recover from that. Unfortunately, that signing by itself has a couple of problems. First of all, the signing means that you have to install a public key on your device to verify that an image is correct. Now, that public key can be wrong for a couple of reasons. One reason is that the signer key, so the private key to make upgrades, that key may expire, so the key has a limited lifetime, and so it can just expire after a while. You can make your key give it infinite lifetime, or very long, like 40 years lifetime, but if you give it a too long lifetime, then there is a high risk that the key gets stolen. The second problem is that you probably want, not probably, but in many situations, you want to give others the possibility to create upgrade files as well. So you have to somehow, you probably don't want to distribute your private key. So you have to give the possibility to add other public keys to your device. And we also don't want to do, people in this room, I hope, will also not want to do devirtualization. So you don't want to completely lock down your system and make it impossible to install something else on it, because the hackers will anyway bypass that and find a way to install something on it. So that you have to add a possibility to install firmware even if the key is not correct or cannot be verified. For that signer expiration, so in case that your private key gets stolen, you should also make it possible to install revocations, so that if a key gets stolen, you can tell your users to upgrade not the firmware but a revocation list. And of course, you also want to give them the possibility to install new public keys without overriding the firmware necessarily. But the important thing is that this also has to be made accessible to the failsafe firmware. So, in the usual case, you're only using your normal firmware. The failsafe firmware never comes into play. But if at some point something goes wrong in the failsafe firmware boots, then this failsafe firmware has access to the current keys and not just the very old key from when the system was first created. So that failsafe firmware, so the keys should be put somewhere in a place where both the failsafe firmware can access it and the normal firmware can access it. I've called that here the config files area, because there are other things that also the failsafe firmware will need to know about, like fixed IP address. This configuration area is of course something that has to be very, very stable. it's like the kernel API. You don't want to change that because otherwise your failsafe firmware fails. Now, another issue with this streaming kind of thing is that you need your entire image in memory, which may be a problem if you don't have enough memory to store an entire image. So to solve that, actually what you will do is split the image in chunks, and write chunk by chunk. And this also gives you the possibility, if something goes wrong somewhere in the middle, you detect that signing is wrong. You don't have to first download the entire upgrade image and then decide, oh, this was not the correct upgrade image. So you can detect it early on and that something is wrong. If it was, for instance, signed with the wrong key, you will detect it even before writing the first block. So you will not first overwrite your entire file system and only then decide this was not a good idea. This early aborting is also useful if you have something else than TCP to transfer your image. If, for instance, it comes over a serial link or a Bluetooth link, then it could be that just some data is lost. And in that case, you also want to detect that early to avoid first putting everything there, overwriting everything, and then noticing that you have to start over. Especially Bluetooth is a pretty slow link, so you don't want to do too much there. And so what I would like to add in guppies, and this will certainly be there on the short term, is a format that supports that chunking and streaming upgrades. So it's a file or stream format, which I call gup, and then some tools to generate and parse the gup format and verify it using GPT. Here's some what it will look like. So it has a header section in the beginning, and then a payload section that's here. There's not much to see there. So it will have in the headers, it will have metadata like how large the upgrade will be, so that you know already beforehand whether you have space in your flash to store it. It will then have a description of all the payloads, the pieces that you want to upgrade. And then there are also hashes, so these basically per chunk there is a hash calculated, and then in the end there is a PGP signature over the header. This PGP signature, because it validates the header, including the hashes, you can just verify the hashes to be sure that your entire upgrade image is correct. This is not a fully secure method, so the really security diehards will not like it, because it's I don't know exactly why, but there is something you can do to make this go wrong. But for the purpose of upgrades, it's good enough, so it works nicely. And then the payloads themselves, you'll see here it starts with a script header. That's because the how to do the upgrade, that will be part of the upgrade stream itself. So the firmware will only contain something to accept an upgrade image, validate it, and then execute it. And this gives you the possibility to do anything you like in there. For instance, when you built the system, you didn't think that you have to be able to update the public keys which are installed in the system. Well, if you have this kind of concept that you execute the upgrade, then you can just put a script in there which will update the public keys and you're done. So putting an executable in your upgrade image gives you the possibility, the freedom to do anything like later on, and avoids that you have to think of all possible upgrades you would want to do while designing your system. This is really an essential thing, and I've heard of many people who had to do strange things to avoid problems because they didn't have this feature. So even if you don't have this, for instance, you can instead have a firmware image which includes a boot script that checks if a certain file exists, and if it doesn't exist, then it will create it. But it's all much more complex than just executing an upgrade image. Now, up to now, I've always assumed that we're upgrading the firmware itself, which is also what we will usually do. However, sometimes it may be necessary to upgrade the bootloader. So how do we do that? Well, we don't. Because if the bootloader is broken, then nothing will work anymore. So the upgrading the bootloader, it's impossible to do safely. Solution is very simple. If you don't put bugs in your bootloader, then the bootloader will also not need to be upgraded. This sounds crazy, but actually you can come close to that by not putting features in your bootloader. So keep your bootloader as simple as possible. Don't make it graphical. Just make it very simple. The only thing it has to do is choose whether you use this image or that image or that image. It doesn't have to do anything more than choosing between 1, 2, or 3 firmware images to boot. If you so to remove features from the bootloader, the fancy features of the bootloader, they're essential and nice to have during development. During development, you want to be able to do TFTP boot, which means you need a network driver in the bootloader. During development, you want to boot from an SD card, which means you need an SD card driver in your bootloader. But in the field, you don't need all that stuff. The one that goes into the field should be as simple as possible. Maybe it's still the same code, but don't rely on it. And also, for the upgrade itself, avoid putting intelligence about upgrades in the bootloader, because then it means if you it means there's more chance of something going wrong in the bootloader. Now, there is still a way out to still be able to recover from a failed upgrade of the bootloader, but it's kind of a wacky construct which I've never seen working in practice. And that is, on almost all platforms, you have something which comes even before the bootloader, which is in ROM, which you can't override, so you can't do anything wrong with it. And typically, you will ignore that piece of firmware. It just boots one thing all the time, so it boots from none, for instance. But you could install a second thing to boot from. For instance, instead of none, on serial flash, something very slow. And then put also your failsafe firmware in that serial flash. And then extra bootloader, failsafe bootloader. Now, when you want to upgrade the bootloader, you start destroying it. If at that point the system reboots because of power failure, for instance, the wrong bootloader will not go to the non-flash because there is nothing in there. And, it will typically detect if there is a certain signature to decide if it can boot from that. And then it falls back to the other boot device, and there you go to the failsafe firmware. And so to do your upgrade, you write your new bootloader, but with that writing you have to take care that you don't write it in the usual way, but you write it starting from somewhere else in the beginning. Why? Because the bootloader will typically check for a signature in the beginning. It will check whether there's typically it's a size in an offset or something like that, which is in the beginning. The long bootloader checks for that. If it's not present, then it will not boot from there. So if you would start writing from the beginning, then it is there, and bootloader will boot from a half-written image, which you don't want. And then in the end, if everything went well, then you can start write the signature in that game. This does not work well in practice because that means that you have to write your pages in non-small sequentially, which has all kinds of issues with non-small supporting that. So it's, as I said, a wacky idea. The final thing I would like to talk about is package-based upgrade. A lot of text, I'm sorry for that. Basically, my main message is stay away from it. Package-based upgrades are not ideal for embedded systems. So there are package managers that you can use. Actually, no package or typical embedded upgrade package systems. And there is one advantage that they have, that is that they allow you to have smaller upgrade files, because you just upgrade the things that have changed. The problem with it is that it's very difficult to predict what exactly is installed. You have one user who has installed upgrade A, B, and C, but another one has only installed A and C, and not B. So to solve that, you shouldn't rely on dependencies or on a list of packages or anything to do that upgrade. If you use package-based upgrade, then you have to make sure that your upgrade scripts will verify that this package is installed at that version, this package is installed at that version, and doesn't try to make a mix and match solution. A second thing is, problem is that by using package upgrades, there are more places where something can go wrong, because a package-based system will typically do more than just overwriting some files. It will overwrite some files, it will delete some files, but in which order will that happen? It will maybe run some script to stop a daemon before overwriting the library that the daemon is using. In principle, the packager has thought about doing this in the right way so that it's atomic and that even if the power is pulled in the middle, it will still work. But because it's adding complexity, there is more chance that something goes wrong. And then, of course, if something goes wrong, for instance, while you're extracting the files from the package, and you have only extracted half of the files, then maybe you've extracted the executable, but not yet the library that the executable is using. And so next time you boot, you will have an executable which will not work. There is a way around that, and that is to make things more atomic, the way that NixOS is doing, and there is also another way to do it. I'll come back to that. NixOS is a not very well known distro, which is a bit Gentoo-like in the sense that it basically builds everything from source. And what you do in NixOS is that installation is not done in user bin, etc. Installation is instead done in directory which is specific for the package you're installing. And not just specific for the package, but also the version. And the version is coded as a SHA. So if you change anything, you will get a unique directory. And then you have the path pointing to all the bin directories for the different packages to make sure that you will find the executable that you need. And there is reference to the publications that explain why this works. So this does make it atomic. And so this way this is one way to avoid problems with package managers. I don't know if it's applicable for embedded systems because this was really designed for servers. So it could be that there is some overhead there that you don't want. Another option is to use unions. The idea of a unified file system is that instead of having a single file system, you have a stack of file systems. For instance, an original root file system, and then an overlay which adds extra packages, and then a temporary file system so that your file system becomes read-writable. And then when you access a file, the union file system will look if the file is present here. If it's not there, it will look if it's here. If it's not there, it will look it's here. So you get a kind of versioning on top of that. And then deletion of files is also handled in a special way in those file systems. There are currently 3 implementations of that, none of which is perfect, so that's life. AOFS has the most features, but its implementation is unreadable, and so it will never get accepted upstream, so it's patches to the kernel. UniFS doesn't have many features, and it even is not anymore developed as a kernel patch. Instead, it's developed as a fuse thing, so it's deciding in which layer you have to go is decided in user space. And a union mount is a thing that will go in the kernel. I think the last time it was posted was in September, so I don't know when it will finally end up in the kernel, but this one will probably end up in the kernel at some point.
How about overlay-FS?
I don't know overlay-FS.
Overlay-FS might have a chance of getting merged as well, and it's the one that requires the least amount of code changes. And
it's also a separate file system.
It's patches, yeah. It's on the file system level, so it's a stackable file system.
Yeah, okay, overlay-FS. If I ever give this presentation again, I will add it.
It works quite well.
So how do you work with this? Well, you have your old stack, which you're still using, and then you use your package manager to add files to a new file system. So you create either a new directory or really a new file system image somewhere in your storage, and you do your package manager stuff in there, and then finally you switch those two. Now that switching is a difficult thing. With AOFS you can really do it atomically at runtime that you swap the two. In practice the easiest is to just reboot the system and use the swap thing. And so in Guppies there is already, that's the one thing that is there, a script to union mount at boot time using UniFS fuse, but you can use the other ones as well, of course. And so it uses the overlay at boot time, so with command line, you tell the script which file systems have to be stacked together. So, if you want to make your upgrade safe, and you really want to do that, then you have to take into account what can go wrong during the upgrade. So you have to think about that your firmware can be bad, that power can fail during the upgrade, that there can be something wrong in the communication. That's something that I didn't mention yet, is that flash can get corrupted because you're writing flash. To make things flexible, because you can't think of everything beforehand, you should put as much as possible in the upgrade file itself, and put as little as intelligence as possible in the firmware. So the firmware should just accept the upgrade image, validate it, and execute it. And also as little as possible intelligence in the bootloader. So the bootloader should just do try that, try that, try that. Unfortunately, there is no single thing that works for everybody because it depends on bootloader, it depends on file system you use, it depends on the hardware for the watchdog. There are too many variables, but there is some common infrastructure that I'm trying to collect in the Guppies project. And if you use this stuff, then hopefully you can make an upgrade system that avoids putting very expensive bricks in the middle of the ocean. Are there questions? Yeah.
On upgrading the bootloader, you're relying on the CPU feature that it can boot from different storage locations. Why wouldn't you split up the bootloader in a first stage and a second stage, and then have the ability to install 2 second stages, which you can verify independently?
Yeah, so the question is, for the bootloader upgrade, why instead of relying on a ROM bootloader, why don't you just have a first stage bootloader and a second stage bootloader, so that you can have a fallback for the second stage bootloader? You could do that, but then why do you have a second stage bootloader in the first place? Because the first stage bootloader already does everything that you need. It can decide whether to use the normal or the fallback second stage bootloader. And that's all you need from a bootloader.
And what if
So-
you want to upgrade the first part of the...
Pardon?
No, but what if you want to upgrade the first part?
And then
of the-
also, yeah, the interesting features like setting up SDRAM, that's in the first stage bootloader, so you would want to upgrade that.
Yeah, but
There-
well,
That said, there may be use cases for that.
You always need N+1.
But the use case would probably be that your second stage bootloader is actually a small kernel that does a gay exec of the real thing. That's, for instance, a use case that I can see that would happen, because in your small kernel you can have drivers, etc., to handle things which are not currently handled by bootloaders like LVM stuff, for instance. Other question?
What's the reason you put the conf partition and the failsafe at the end of the file of your flash layout?
No, the order doesn't mean anything.
Okay.
Just separate. Yeah.
Do you see any special reason for keeping the initial part you started about putting into persistent storage if you are putting the one or the other? Because the next part of your failsafe, you actually did something which, as I see it, makes it redundant. So if you're able to handle a bad firmware, how is that? Why is that not enough? Because if it fails during upgrade in the initial stage, then it will be a bad firmware, and it will be handled by the other solution.
That could be right. I have to think about that. So the question was, instead of atomically changing which image to boot in a bootloader, why not just rely on the handling of bad firmware, so on detecting one-shot timeouts, and use that to decide to go to the second one. That's probably going to solve it as well.
Then you reduce some of the complexity.
So, yeah. Nice, I can give this presentation again with different content. Other questions? Yes?
What about scenarios where you don't have so much flash, where you can put maybe two bootloaders and failsafe bootloader? Because it's pretty much if you just care about BOM for the price of the flash. So can you just deal with one bootloader and compress the image for the root FS or such? Where do you support also some different schemes for this other startup sequence or not?
So let me check if I So the question is, why do you need so many partitions?
Yeah, but whether you need so many partitions by design or it's just whether it's flexible or not. Because we did different scan. We have just one big partition and just downloaded image as separate partition. And the upgrade mechanism can use the prepared download partition to replace the FS, and it has smaller footprint in the flash. But I was just interested whether what you presented here is the only scheme how you fail-safe, how you start.
So I still don't fully understand what you're saying.
Well, did you consider something like, okay, you have current firmware, and you have another partition where you can download just the image from the web?
Yeah. So as I understand what you're saying is, instead of having two versions of firmware, you can have here just a temporary storage to download your upgrade image.
And you don't need fail-safe, just bootloader and this boot partition.
But then, if you have that, you still have to somehow copy it to there, or switch bootloader from one to the other, right?
Yes, you cannot switch. It's just raw image. You cannot put it. You must copy it into the.
Yeah, but if you have to copy it, then something can go wrong during the copying. If then you don't have a fail-safe, you're dead. So it's better to and easier to just override your firmware. Then you don't only need one, you don't need it twice. And you need a very small fail-safe that you can fall back to in case something goes wrong to the override. If your firmware itself, the root file system, you can't do live overrides, then you can also first boot to the failsafe firmware, and let the failsafe firmware do the write. That's another option. Okay.
But maybe you just said it, but you can't overwrite your firmware, your file system while it is booted.
Well, again, that depends. So, if you can overwrite your file system while it's running, for instance, if you don't have a file system but just an init.rd image, which is extracted into a temp-fs, then you can live with this and just overwrite your so-called running system because it's not actually executed in place. The kernel itself, for instance, you can always overwrite that while it is running because it's copied from the storage to the memory before it's executed. If you don't want that, you can have two, and then you will, when you're running this firmware, you will upgrade this partition with the new firmware. And if you're running this firmware, you will upgrade this partition with the new firmware. Okay. More questions? Yeah.
You propose the failsafe to be small Linux also?
Yes. So the failsafe, I think, it's a small Linux, which is actually typically the same firmware as here, but stripping out everything that you don't need to do upgrades. So removing queues, removing the drivers for things that you don't need to do upgrades, and removing the application software.
There's also
of course, only if that makes sense. Eh? Sometimes you don't reduce the size by removing your own application, so yeah, then it's best to just have 2 copies of the full firmware. Yeah?
There's also option that you always boot the failsafe, and it checks if the firmware is proper, and if it is proper, then it can boot the firmware.
Yeah, so you could always boot the failsafe, and then
validate.
Let the failsafe validate the rest. So then you use the failsafe as a bootloader, in a way. Yeah. That's something that you can do if your bootloader cannot validate, for some reason cannot validate the firmware. But so I assume that your bootloader has the capabilities to validate the firmware. Yeah?
Why not to update the firmware exclusively from failsafe firmware?
Yeah, so it is a possibility to, instead of overwriting the firmware as it is running, you can first reboot or exec to the failsafe firmware and let that do the actual upgrade.
Why can't? Why not to do it?
Yeah, so you can do that.
More simple system.
You can do it. It simplifies your system, but it means that it's more complex to.
It means longer downtime.
It's a longer downtime, of course, because your system has to go down before you can start an upgrade. And also, it's more complex to have some kinds of interactions. So, for instance, your upgrade could be started by somebody clicking on a web page, start upgrade. But if you then reboot, then you lose your network connection. You have to restart the web server in the new in failsafe firmware. That new the client has to reconnect to that new web server to see now it's running. Only then it can start uploading the image. So some situations become more complex that way. Yeah.
If the firmwares were written in a read-only file system, do you really need the failsafe yet? Because if you are not upgrading that, writing to the file system, they are just read-only, then you can update one, you always will have one stable firmware.
So the baseline is, that's why I say everything depends and there is no generic mechanism. There are several ways that you can use failsafes and fallbacks. You can have one big firmware and then a backup failsafe firmware, or you can have one big firmware and then a backup firmware, just so that you always have something running, but still a failsafe firmware just in case. But if you anyway have two, they can just have those two and discard the failsafe. So there are many possibilities. You could have 3 known goods, I mean 2 known goods, even. Yeah.
But actually, you can have these 2 firmwares where you simply, as we say, now switch it always, so you always upgrade the other one. They could even have both have a read-write root file system, but if they also come with a read-only inaccessible test, which contains your failsafe code, then you can actually, you don't really need the failsafe, although it's always nicer to have more failsafe, but that way you always have.
So one possibility to avoid the failsafe is to have an init ramifs, which is always there, which is actually the failsafe. But that doesn't solve the problem if you upgrade the kernel.
No, but as you have 2, so you upgrade the kernel and then you have the old one, which both.
The reason that I always put here with 2 firmware images that still have a failsafe is because it's very difficult to know that, to be sure that the known good is actually good. So you think that it's good, but it can be that after a long time you discover that there is a bug in the kernel, for instance. And having a failsafe then allows you to fall back on that at least. Although, admittedly, chances are that the failsafe will then also be broken, so it's not necessarily a solution.
The failsafe never gets updated in your
You could actually update the failsafe as well, but then it really becomes the same as having 2 firmwares.
You should never update the failsafe.
Yeah. Okay, thank you.